Hey, well, that's 11. I hope everyone can hear me. Good morning, everyone, and welcome to today's webinar, Forage Fertility on the Prairies. My name is Luke Jorgensen. I'm a Range Management Extension Specialist with the Ministry of Agriculture based in Weyburn, and I'll chair today's session. We're pleased to have Dr. Jeff Schoenau with us this morning to share his expertise on fertility management in forage systems. His decades of research and practical knowledge offer valuable insights for producers and others working in the agriculture industry who are looking to improve forage productivity and sustainability. I would like to promote another upcoming webinar that we have. It's called Brush Management on the Prairies, and it'll take place on Tuesday, April 15th at 12 o'clock noon. This session will explore practical strategies for managing woody species encroachment in pasture and rangeland systems. A few quick housekeeping notes. All attendees are muted throughout the presentation to make sure we have a clear audio. If you have questions during the presentation or afterwards, we'll have some time for questions after. Please type them into the question box located in the bottom right of your control panel. So we'll be able to see these, and then at the end, we'll field them to Dr. Schoenau. Questions are submitted anonymously and will be addressed during the Q&A at the end. This webinar is being recorded, and we'll be sending a follow-up email with the link later today. And I'll send you all a survey by email after the session. We appreciate your feedback, and it helps us guide future extension programming and research priorities. So I'm pleased to introduce today's speaker, Dr. Jeff Schoenau, Professor of Soil Science at the University of Saskatchewan. Dr. Schoenau has been a leader in soil fertility and nutrient management for over 25 years, working extensively with prairie agroecosystems. Today, he'll be presenting strategies for improving fertility in grass and legume forage stands, with an emphasis on practical applications for prairie producers. Without further ado, I will give Dr. Schoenau the presentation screen.
Perfect. All right. Hope everybody can see my presentation. All right. Think so. Sounds like it. I don't see anybody indicating any problems. So hey, it's really great to be here this morning and to talk to you folks on this bright sunny morning about a little bit about forage fertility management. And I guess the first thing I'd like to start out with is certainly to make folks aware that forage crops do require a fair bit of nutrient. And this is some crop nutrient removal table here from the Canadian Fertilizer Institute from a few years back. And I think it does a really nice job of showing for good alfalfa stand and a good grass stand just how much nitrogen, phosphorus, potassium, and sulfur is in the above ground material. And I think if we look first at the alfalfa there, a pretty good crop of alfalfa there, 5 tons per acre, about 300 pounds of nitrogen per acre is in that above ground material. Now, luckily, as I'll talk about, a lot of that nitrogen, in fact, most of it, can come from the air through biological fixation. But you can see there as we move over, and I'm just going to grab my pointer here. There we are. Yeah. You can see that there's also a lot of phosphorus, potassium, and sulfur in that above ground material that has to come from the soil. And if we look below at the grass, 3 tons per acre of a grass stand, we've got maybe 100 pounds of nitrogen per acre in that above ground material that we would remove in harvest. And of course, in the case of a pure grass stand, all of that has to come from the soil. And then we've got a fair bit of phosphorus, potassium, and sulfur in there as well. So I think we can see when we take all of that above ground material off with haying over time, taking a fair bit of hay off of there every year, does remove a lot of nutrient. And if we're not replenishing that with fertilizer or manure, we do find that forage production declines largely due to a lack of fertility. And in fact, when it comes to rejuvenation of an old, tired forage stand, in many cases, you can bring that stand back to life through the addition of some nutrients, either fertilizer and or manure. And indeed, what we have in terms of a forage stand and its crop nutrition also will affect the soil nutrient supply that we may see to a following crop that you would grow in rotation after you terminate that forage. So we really need to be thinking about forage fertility, folks, in both the short term, upcoming season, and also longer term over several years, considerations of nutrient management and making sure that we've got enough to optimize our forage production and quality, and also over the long term to maintain the productivity by putting back in what we're taking out. And I think really a very important part of that is capitalizing on this process of biological nitrogen fixations that legumes do. And this is also important in mixed legume grass stands as well as pure legume stands as well. So I want to start out a little bit by taking a look at this biological nitrogen fixation process. And I'm using this slide I borrowed from Dr. Fran Wally, who's retired now, but did a whole lot of work on biological nitrogen fixation and inoculants over the year, but really showing that, it really all starts there in the roots of that legume, those nodules that are the home for those rhizobium bacteria that are capable of fixing nitrogen from the air and providing it to the plant in exchange for food. So it's what we call a symbiosis. It's a two-way street. Both partners benefit, the bacteria and the plant. So the plant has to give up some energy, some photosynthate to the bacteria in that nodule, some food for them to grow. And what the bacteria then do, the rhizobia, they produce an enzyme that allows the conversion of gaseous nitrogen in the air. The atmosphere is 78% N2 by weight. It's unusable by a plant until we've got that bacteria that produces that enzyme that will convert that dinitrogen gas in the air to plant usable nitrogen, to ammonia that then gets transferred to the plant. And it's a two-way street, it's a symbiosis, and really, folks, anything that affects the plant negatively is going to negatively affect nitrogen fixation. So things like drought, temperature stress, too much, too little water is going to influence nitrogen fixation adversely if it adversely affects the plant. And similarly, some of the conditions that we may encounter in the soil, like acidity, can also have an adverse effect on biological nitrogen fixation, because the rhizobium that are commonly in association with alfalfa roots, for example, do not like soil acidity or low pH. So how much nitrogen do we get from this biological nitrogen fixation and get into that plant through this process? I guess, like a lot of things out there, depends. The answer that you get depends on how you measure it, and it's variable. There's different ways that you can measure the biological nitrogen fixation process and how much it contributes. A technique that we commonly use is called the N15 isotope dilution technique, and I think it's a pretty accurate and sensitive way to measure biological nitrogen fixation. But folks, any way you slice it, it's a pretty significant contribution, especially when you put a dollar value on it in terms of what you would pay for that nitrogen if you were to purchase it from your local fertilizer dealer. And I think we can say, as a kind of a general rule of thumb, about 3/4 on average of the nitrogen in a legume, and that includes forage legumes like alfalfa, clover, as well as our annual legumes, our pulse crops like peas and lentils, about 3/4 of that comes from the atmosphere through this biological fixation process in the nodule on the root. And I'm sure there's folks in the audience, a lot of folks who have maybe done this and taken the roots of a legume, and it's a little bit easier, I think, to do this in some of the annual legumes like peas or lentils or faba beans than it is in alfalfa. But you can take those nodules and you can cut them open. And if you cut them open and you see this nice bright red color there, what that tells you is that plant is actively fixing nitrogen. The rhizobia are active, and the red color there comes from a compound called leg hemoglobin. And we know hemoglobin is what gives your blood the reddish color. Well, it's kind of similar here. We've got this leg hemoglobin that's a reddish color. It's being produced, and what it does is it helps that nitrogenase enzyme be as active as possible. It shields it from oxygen. So we can see there beefy colored pink nodules indicating active nitrogen fixation. How much do we get from the air? Well, I think when we look at the relative amounts of nitrogen derived from legumes by this biological nitrogen fixation, the forage legumes are certainly the king of the hill on top of the heap. Alfalfa, anywhere from maybe 100 to as much as 250 pounds of nitrogen per acre can come from biological fixation. The clovers are not too far behind that. When it comes to annual legumes, faba beans actually are very good nitrogen fixers and tend to produce the greatest amounts of nitrogen through this biological fixation. Peas are pretty good. Soybeans, we can move down the list. Lentils, chickpea, dry bean, the lowest amounts of nitrogen fixed. And maybe this reflects the fact that we really don't have very good inoculants right now for nitrogen fixation from our dry bean crops. How much we actually achieve out there in the field certainly depends on nodulation and the use of commercial inoculants. Rhizobium strains that have been selected for superior nitrogen fixing abilities certainly can be beneficial, proven beneficial in enhancing that contribution from nitrogen fixation. Environmental conditions, as I've spoke about before. Soil available nitrogen also has a very large influence on the amount or proportion of nitrogen that is derived from biological fixation versus from the soil. And when we have lots of available nitrogen in the soil, what happens is the legume doesn't give the food to the rhizobium because it's cheaper energetically for that legume to use the available nitrogen in the soil. So if you grow a legume on a soil that's high in available nitrogen, it'll do fine. It'll just use the available nitrogen in the soil and not carry out the biological nitrogen fixation process. And when that happens, then you're really losing out on that benefit of that external nitrogen coming in from the air into the plant. So you get the most amount of nitrogen fixation when you grow legumes on soils that are low in available nitrogen. But we do need to pay attention to the availability of other nutrients, especially nutrients like phosphorus. Phosphorus is the energy currency of life. Biological nitrogen fixation, folks, is very energy dependent. So we do need to make sure if we're going to get maximum biological nitrogen fixation that we have ample supplies of available phosphorus in the soil. And forage legumes we find are very efficient nitrogen fixers. And this is some work from a recent graduate student who worked with me, Dr. Ghazali Isa. And his work, he was looking at percentage of nitrogen in the forage legume derived from the air. So this is what we call percentage NDFA, percentage of nitrogen derived from biological fixation. And folks, you can see there, alfalfa, in this case, getting more than 90% of the nitrogen in that plant coming from biological nitrogen fixation, which is pretty impressive. Milk vetch, not too far behind, above 85%. And in this particular comparison here, our Sanfoin, a couple of different cultivars coming in around 80%. So all of them above that 3/4 or 75% of the nitrogen coming from the air through fixation. I think the other important observation and findings that Ghazali and others showed in their research work is that when you have this forage legume growing alongside a grass in a forage stand, we get significant amounts of the fixed nitrogen transferred to the companion grass during growth. And this may be as much as 15, 20%, for example, of the nitrogen that's fixed as that forage legume like alfalfa is growing that year. Maybe 20% of the nitrogen gets transferred that year to the grass that's growing along with it. And that's a really important synergy that we observe when we have these legume grass binary combinations growing out there in the field. We also see benefits to the crop that would follow once you terminate that legume stand, and we can divide that into what we call nitrogen benefits and non-nitrogen benefits. And these non-nitrogen benefits actually can be very important, sometimes even more important than the nitrogen benefit. But the fact that when you have a legume, a forage legume in there, it can assist in increasing the availability of other nutrients like phosphorus to a crop that would follow after the alfalfa or clover, also improve tilth or soil structure, and a break in the pest cycle. And really, I go back to some old work that was done by Scott Wright, who's now the director of the Livestock Forage Center of Excellence here at the University of Saskatchewan. But when he was working at Melfort, did some I think very interesting work here that demonstrated really, I think, quite clearly this non-nitrogen benefit. And this is the yield of barley growing on different stubbles, including its own stubble, barley on barley, and then barley on different legume studies. And what this graph shows is, no matter how much nitrogen fertilizer that you added, you still could not achieve the yield of barley growing on barley stubble compared to when it was growing on a legume stubble. And so I think that's a really good example of the non-nitrogen benefit. And I guess what I've sometimes termed the magic of legumes in rotation and the good things that they do for the soil and the soil health. And some of that non-nitrogen benefit may relate to soil phosphorus fertility. And the thing about legumes is they're really good scavengers for phosphorus in the soil, as well as other nutrients like potassium and sulfur. And legumes in particular with phosphorus can solubilize phosphorus, make it more soluble through the action of acidifying the area around its roots. Also, they're highly mycorrhizal. They have this beneficial relationship with the fungi, which extends the rooting system, and that's really important in enabling a crop to access phosphorus. And the other thing is that the forage legumes like alfalfa, clover, we know they have deep rooting systems. And because of that, when those roots get down deep, they can solubilize and mobilize some of the phosphorus minerals that are contained in our parent material down in those sea horizons, those deep horizons, and bring it up to the surface for recycling. And some of our research work that we conducted across Saskatchewan a few years ago showed this ability of having a alfalfa or sweet clover in rotation for a couple of years help to increase the mobilization of soil phosphorus and maintain available phosphorus levels in the surface soil in the face of some fairly high removal of phosphorus through the haying and the removal of the above ground biomass of those forage legumes. And certainly that when you even look at the roots, you realize, you think about wheat with a fibrous root system, canola with a kind of combination tap plus fibrous, and then you got flax with a tap root. That taproot still doesn't get down as deep as what we see here with the taproots of alfalfa, which can get down several feet in the soil profile and access nutrients and water. I'd like to talk a little bit about some of our most recent research work, really attempting to capitalize on the value of having legumes, in particular having forage legumes growing alongside of grass. And that's some work that's just ongoing, and with a graduate student, Mason Plews, as his MSc project, working with myself and Dr. Bill Agitu from the Plant Science Department, looking at sod seeding to introduce forage legumes into into a grass-dominated system. And so this is work that's carried out at living lab sites in Saskatchewan, East Central at Touchwood Hills, and also in the southwest at Elrose and Morse. And I'd just like to share with you a little bit of Mason's data here on plant establishment. This was some work that was done at the Touchwood Hills Ducks Unlimited Ranch. Here looking at different suppression methods, grass suppression methods to enhance the establishment of sod-seeded legumes. And we had purple alfalfa, sandfoin, and yellow alfalfa. And I think what this shows here, this graph, you're looking at seeding in the fall, late fall seeding when the grass is somewhat dormant, and then a herbicide suppression with glyphosate that was applied, I believe, about 0.9 liters per acre. That was a 540 active ingredient product. And then where the grass was mowed, and then where it was simply seeded into the grass in the spring. And I think what this shows in this 2024 data of Mason's, that the sod-seeded legume establishment was best with the herbicide suppression. So that you do need to get some type of a suppression there, and this seemed to work the best in this instance in order to get that alfalfa growing there. And now what Mason's doing is he's following up what's the impact of that on the forage yield and the forage quality. I'm going to switch gears a little bit and talk a little bit about forage fertilizer nutrient needs and kind of some of the short-term considerations. And as I've said before and stress again, is that a lot of the forage fields out there are under-fertilized and indeed nutrient deficient. And we really do have the opportunity for rejuvenation of these stands by getting some nutrient back in there. And so we find, in particular, the hayed stands, hayed grass stands are frequently nitrogen, phosphorus deficient, and sometimes even, depending on where you are, especially if you're in sandy soils, eroded soils, up in the northern agricultural soils, there in the gray soil climatic zone, also sometimes potassium, sulfur, and even occasionally micronutrient deficient. And that's especially if you've taken some big hay yields off of there and exported a lot of that nutrient out of there without any type of replacement. And so interesting, I had the opportunity a few years back to take a look at a number of different forage fields across Saskatchewan, and actually a lot of those forage fields tested in single-digit parts per million, and also very low supply rates if folks were using PRS probe technique for assessing available phosphorus, very low compared to the critical level at which no response generally occurs, which is for most soil test extractants like the Olsen test around 30 ppm. So certainly a lot of those forage fields are lacking in phosphorus. So if we think about phosphorus in particular, again, thinking short-term, long-term fertility considerations, what's needed this year, what do I need to be putting on, if you're thinking long-term, to put back in what I'm taking out. And I think some kinds of general rules of thumb in we're thinking about fertilizing stands of grass, fertilizing stand of legume, and in most cases a kind of mixed stand, grass legume stand. I think a good general rule of thumb is that if you've got a grass legume stand with more than about 50% legume in there, you're not going to see a big response to nitrogen fertilization. And we've observed that this is the case with both commercial fertilizer nitrogen and also with nitrogen that's added as manure, for example, liquid swine manure. If it's a stand that's dominated by alfalfa or pure alfalfa, you see very little response to added nitrogen. And that is because, as I spoke about earlier, that legume will fix that nitrogen if it's not available in the soil. And if you do make it available by adding fertilizer, the legume will simply use the available nitrogen in lieu of carrying out fixation. And either way, the legume will do fine. And overall, not much effect of the nitrogen fertilization, but it does shift it to the plant using the nitrogen in the soil that you've added as fertilizer, as opposed to getting it for free, so to speak, from the air. If you've got a mixed stand, on the other hand, that contains a lot of legume and looking at phosphorus, those mixed stands do often respond better, and certainly pure legume stands, to applied phosphorus than a pure grass stand alone. And I think this reflects the fact that those legumes do have high phosphorus requirements. And if you're talking about phosphorus fertilization of a grass-dominated stand, here we observe in our trials, and this has been, I think, documented for quite some time, is that just adding phosphorus alone to a grass stand often doesn't elicit much response, even if it comes out fairly deficient according to a soil test extraction. And really, when you do tend to see a response to that phosphorus, typically it coincides with also adding a fairly high rate of nitrogen as well. And I think that's partly because in a lot of these grass stands or grass dominated stands, it's lack of nitrogen that's really holding back the yield of that stand. I guess when it comes to fertility, phosphorus fertility management in any type of forage, I think a good strategy to ensure the longevity and adequate phosphorus nutrition of that stand, folks, is actually to start out when you're establishing the stand to add enough phosphorus at that time that it's going to last for the duration of that stand, rather than trying to come in and add phosphorus later through a broadcast application. Because a broadcast application of phosphorus is not particularly efficient over the short term. And that's because phosphorus is immobile in the soil. It tends to get hung up in the surface. You've got some surface feeder roots there, but it is going to take a while for that phosphorus to get down to where those deeper roots are and be able to be utilized by the plant. And that balance of inputs versus outputs, and considering that, folks, I think is important when you're looking at maintaining long-term fertility of nutrients like phosphorus, potassium, sulfur. And I think this chart here, I think, demonstrates really quite nicely in the case of soil available phosphorus, the effects of adding different amounts of phosphorus and its influence on the soil test for phosphorus, the soil test level. And I guess not surprisingly, if you're not adding any phosphorus at all, you're going to, and this is a case after 8 years, maybe deplete that soil test phosphorus level by as much as 10 or 15 parts per million. If you're up in this 40 level, you're keeping it about the same. If you want to build or increase your soil test available phosphorus or your phosphorus fertility of the soil, you put on more than what you're taking out. So can you build soil phosphorus fertility by adding more phosphorus than what you're taking out in harvest? Yeah, you can. And actually, building soil phosphorus fertility works really quite well because phosphorus is really not susceptible to the kind of gaseous losses like nitrogen is or leaching losses, but it's still a slow process. And available phosphorus, as I say there, do not change rapidly, and it may take a few years to get to your target level of soil available phosphorus that indicates sufficiency. And I guess I put together for folks a kind of a general rule coming out of a review paper by Grant and Flayton that if you're looking at rates, the rate of what we would call surplus P, that's phosphorus applied as fertilizer, subtracting the amount of phosphorus that you're taking out, the surplus P that you need to raise your soil test, your extractable P by 1 parts per million after harvest, ranges anywhere from 20 to 40 P2O5 per acre. So as you can see, you either need to add a huge amount to build it up by build that soil test level by a large amount. Smaller amounts, it's a slow, gradual increase that you can expect to see, but it will occur over time. And you may be wondering, well, how much phosphorus or how much nutrient in general is removed in harvested grain and forage if you're doing these kinds of long-term balance calculations, amounts in, amounts out, and what am I taking out, and what do I need to be thinking about putting back in to maintain fertility? A couple of tools out there. One is the Prairie Nutrient Removal Calculator, which calculates for different crops based on grain yield, how much nutrient is removed in the grain. And this is available online. You type that in, you're able to access that in a matter of seconds, get numbers for any crop that you're looking at for grain removal. If you're looking at the amount of nutrient removed in forage or straw, a very useful tool is the Forage and Crop Nutrient Value Calculator. That's a simple Excel program developed by the Ministry of Agriculture that allows you to determine nutrient removal and what the value of that is based on value or costs of fertilizer nutrients that you can get for your commercial fertilizers. I guess we've been talking about nitrogen and phosphorus. We also need to be thinking about other nutrients as well, other macros like potassium. Legumes do have high potassium requirements. Potassium deficiency, certainly not as big an issue in southern Saskatchewan as it is in the soils in the north, especially some of the sandy gray soils. Potassium fertilization, particularly in those kinds of soils, work done at the Melfort Ag Canada Research Station a few years ago, showing the benefits of good potassium fertility on increasing not only yield, but also protein content, and even reducing the winter kill of alfalfa. I guess following that adage, a well-nourished plant is a healthy plant. It's a tough plant, able to better off, fend off, have resilience against different stresses. Sulfur might be a limitation, and here I say especially pay attention to mixed stands, alfalfa, and that again reflects that forage legumes do have high sulfur requirements, and the kinds of soils particularly where a large drawdown year after year after year from cutting high yields of alfalfa or another forage legume would be on these sandy textured gray soils which have quite low sulfur fertility to begin with. And Micronutrient deficiency, although relatively isolated, could be a factor. Alfalfa growing on sandy, low organic matter, high pH soils. Occasionally, boron deficiency may show up on, in some instances, with alfalfa on these very low testing boron soils that are most likely to be countered under sandy texture, low organic matter, and high pH. And always like to stress the importance of a balanced nutrition. A balanced nutrition for both maximum yield and quality. Some work that was done in northeastern Saskatchewan a few years ago, I was involved with. This was with Timothy grass. When you apply nitrogen alone, phosphorus alone, sulfur alone, you got some yield benefit. And even if you combine phosphorus and sulfur together, yeah, you got some increase in the yield of Timothy over the unfertilized control. But where we saw the highest forage yield and quality was when the nitrogen, sulfur, and phosphorus fertilizer were applied together in the appropriate balance required to address all of those limitations. So yeah, balanced fertility is important. Moisture is important as well, and so you often see recommendations for forage fertilizer based on general moisture availability, crop yield potential estimates, which vary according to the soil zone. Brown soil zone, drier environment, 10 to 15 pounds of forage yield increase per pound of N applied. Black soil zone, wetter environment, greater yield potential, 20 to 30 pounds of forage yield increase per pound of nitrogen per acre applied. So certainly, what you're going to see for that yield response, as we know in the prairies, very much dependent on what you're going to have for available moisture. A question that folks may ask sometimes: when should I fertilize the forage stand? And I guess I would say late fall, early spring is a pretty good time to fertilize the forage stand, especially for nitrogen, because when the soils have cooled down, as in late fall or early spring, that slows the activity of an enzyme called urease, which is responsible for volatile losses of ammonia when urea is broadcast on the surface. So applying nitrogen, if you're broadcasting urea, if the soil is cool, that's going to help reduce volatile losses of nitrogen. And also at that time of the year, often we anticipate some snowmelt, some rainfall that's going to help to rapidly move that broadcast nitrogen into the soil. On the subject of fertilizer application method, if you're just broadcasting regular urea 4600 without any kind of enhanced efficiency additive, we may anticipate large losses of nitrogen through ammonia volatilization if the urea is simply spread on the surface. And that's because there's lots of this urease enzyme in that thatch of that forage that will result in conversion of the urea to ammonia rapidly. And if it's sitting there on the surface, that ammonia has nowhere to go but up into the air and be lost. Strategies to deal with this: well, I guess if you can anticipate a rainfall that's going to come shortly after application of your urea, that's going to help move that urea into the soil. Once it's in the soil and the hydrolysis takes place and the ammonia is produced, it's retained in the soil by conversion to ammonium. But if you're putting it on the surface, a granular source like ammonium nitrate, I know I'm probably not going to be able to get that anymore, but ammonium nitrate or ammonium sulfate would be better for broadcast in reducing the ammonia volatilization loss potential. Of course, with ammonium sulfate, you're paying for both nitrogen and sulfur in there that you may not need. I think a very good strategy when you are broadcasting urea onto a forage stand, a grass stand, to supply nitrogen is to treat that urea with a urease inhibitor. Example, there's a number of different products out there, a couple of examples: Agritane, Limus. This urease inhibitor inhibits the activity of that urease enzyme for a period of time, maybe a couple of weeks, and that gives an opportunity for rain to come along, wash that urea into that soil, and reduce volatile ammonia loss. Another strategy, and this is one that we researched a few years ago, dribble banding on UAN solution, 2800. And I think we showed that could be pretty effective, especially if you've got a rain after application, to move that nitrogen into the soil. Dribble banding onto the surface. And the other treatment that we had was actually coultering the 2800 liquid nitrogen into the soil. And this is some of the data that came out of our work. This was on meadow brome grass stand at Meacham in east of Saskatoon here. And I think what this shows is overall a pretty darn good yield response to about 50 pounds of nitrogen per acre that was applied as UAN solution, a near doubling of the dry matter yield of that meadow brome grass. And I think the other interesting thing that showed up at this site, as well as our other sites, is that comparing coultering in with the disc versus simply dribble banding that urea ammonium nitrate on the surface of that grass, actually there was very little difference in the yield or the nitrogen recovery. Now, granted, at all of our sites, within a week, we had a rain that helped move that nitrogen into the soil, but that surface dribble banding is a pretty economical way in terms of application equipment to put that nitrogen into the soil without having to worry about disking it in and hitting rocks and bouncing around your equipment in the soil across that field. And as shown there, we got some pretty impressive results there in our work, not only in yield increase, but also in protein content. And that protein, that increase in quality, is also another benefit, particularly from nitrogen fertilization. We can see there, folks, that addition of about 30 to 50 pounds of nitrogen per acre dribble banded onto the surface, in some cases nearly doubled the yield, and also resulted in a substantial increase in protein content. Beyond that, increasing rates of nitrogen, we could have to some really high rates here, tended to have very little influence on increasing the yield above the low rate, but did increase the protein content. And I'll also say this really high rate actually persisted. We had beneficial effects not only in the year of application, but also a carryover into subsequent years. So when you're doing the economic analysis, that has to be factored in as well. I'll move away from commercial fertilizers and talk a little bit next about manures. Manure is a very valuable way to return nutrient and fertilize forage stands. And first, liquid manures. And I guess when it comes to liquid manure, whether you're talking about liquid swine manure, liquid dairy manure, really you want to get it in the ground. Inject it to reduce odor, reduce the nutrient loss, and increase recovery. And certainly as we worked with in particular liquid swine manure over a number of years, showed the benefit of injecting that soil or injecting that manure into the soil, getting it down where the roots were to improve the access and also reduce the gaseous losses. And there's a lot of good equipment out there that allows you to do that. In fact, low disturbance disc type units or a unit like this airway unit up here at the top that creates pockets in the soil into which that liquid manure can be injected with relatively little disturbance to the forage stand. And working at some very nutrient deficient sites, especially very nitrogen deficient sites a few years back in east central Saskatchewan. One stand here, there's a crested wheat stand here, put on 3,300 gallons per acre of injected liquid swine manure in the fall. And you can see in the spring there how that plot was greening up compared to the rest of that stand. That's largely attributable to the nitrogen, but also the other nutrients in that liquid manure like phosphorus, potassium, some sulfur, even the micros are a contributing factor to that yield benefit in those old stands. And just to put some numbers to this, showing here, this is the above ground biomass in this old crested wheat stand, putting on 6,600 gallons per acre of liquid swine manure, injecting it. We were able to quadruple the above ground biomass yield and increase the seed yield of that crested wheat tenfold. Some very impressive responses of those old nutrient deficient grass stands to that injected liquid swine manure. Really a great way to rejuvenate the stand. And finally, solid manures and forages. Solid manures, different than liquid manures. The solid manures that we have available to us on the Canadian prairies here, cattle penning manures, we tend to consider those to be slow release sources of nutrient, especially the cattle penning manure that's got a lot of straw bedding material mixed in with the fecal material. That results in a fairly high what we call carbon to nitrogen ratio, meaning that the microorganisms have to chew through a fair bit of carbon in order to release the nitrogen. So nitrogen release is quite slowly from cattle penning manure applied to fields. And if you think about going out into the field and surface applying cattle manure, penning manure on top of a forage stand, that surface placement tends to slow that nutrient release even more and reduce the nutrient recovery. So I think that, you know, what this led to was an interest in a comparison. Well, what about when you feed the animals in the field? How does that compare to hauling manure out of a yard and applying it out in the field on the surface of that forage stand? And certainly in-field feeding can be a more effective approach to nutrient recycling and forage response. And this really comes back to that when you feed animals in a pen, overwinter them in a pen and feed them, you do lose a fair bit more nutrient, especially nitrogen that comes from the urine gets lost to a much greater extent when it's fed in the yard in a pen versus deposited out there directly in the field by the animals. And we wanted to put some numbers to this in some work. So myself and Bard Lardner worked with a graduate student, Paul Yanishu, who did a study and was interested in this nutrient cycling, recovery, and retention when you fed cattle in field versus hauling the manure out of the pen and applying it using manure spreader on top of that a grass forage stand. And we recognize that in any kind of a feed like a bale, yeah, there's nutrients in there. 1,400-pound hay bale, maybe 30 pounds of N, 5 pounds of phosphorus, 25 pounds of potassium, 3 pounds of sulfur. But that nutrient really doesn't get into the cycle and get going, so to speak, until these four-legged fertilizer factories, as Paul Yanish, the MSc student who worked on this, called the cows there, get going. And the reason why they're fertilizer factories is because only a small proportion, maybe only 10% of the nitrogen that's consumed actually is retained in the animal. The rest of it goes out the other end, mainly as urine. And in the case of phosphorus, only about 20% gets retained. The rest goes out. So when it goes out directly into the field, it gets into the soil and gets recovered back into the forage and becomes part of that cycle. And this is really reflected in what Paul saw in his forage growth as a function of different feeding systems. Where the manure was hauled out of the pens and applied in the field, some yield increase of this Russian wild ryegrass stand yield, but the greatest yield increases were where those animals, equivalent amount of animals, equivalent amount of nutrient in the feed actually got fed in the field, as showing here, both either as bale grazing or as a bale processing system. And those effects from the nutrients excreted in the urine and the fecal material from that infield feeding, as many folks out there are aware, you know, and also the uneaten feed, persist for not only the year afterwards, but can persist for a number of years as well. So Paul put some numbers to this in his thesis research work and looked at the capture of the nutrient in that feed and bedding by the forage in those systems and got some pretty impressive recoveries of the nitrogen and the phosphorus by the forage in the feed that was fed to those animals and deposited directly in the field through the fecal material and the urine. Compared to where the manure was, or compared to where the feed was fed in the yard in a lot, the manure was collected, put into a spreader, hauled out into the field, and spread out in the pasture. They're single digits, only 5 to 9% of the added nitrogen in the feed recovered, only 3 to 5% of the added peat. So basically, folks, a lot more efficient conservation and recycling of feed nutrients when you use the infield feeding system versus the traditional dry lot type of overwintering system. And I think a lot of producers out there, growers, knew this to begin with, and we're actually ahead of the researchers in terms of maybe understanding what was going on, but I think what this research showed was really putting some numbers to it and really documenting that in fact this can be an efficient way of recycling nutrients and indeed getting them back into the field in the greatest proportion where they're needed. I guess the one thing to always think about, though, when you're overwintering animals in the field is think about your overwintering site and where the water's going, particularly the snowmelt runoff. And so as a follow-up study to this, myself and Dr. Lardner had a student who looked at nutrient export in water off of these in-field overwintering sites. And indeed, you do find a lot more phosphorus and nitrogen in that runoff water. So you want to make sure that within your field wintering site, that the water that's running off of there is contained within that field rather than running into some type of sensitive stream or lake where those nutrients can cause a deterioration in water quality. So that means carefully choosing those in-field overwintering sites. So I think to conclude, I think it's kind of a whole nother story, but that I've worked on as well as others a lot. Those forages are very important in improving soil quality, health, organic matter, nutrient supply, but certainly to get the maximum benefit from that perennial forage system in terms of producing a high yield of quality forage and also contributing to good long-term soil health, fertility, and productivity is certainly obtained through good fertility management and using those fertilizer nutrients and manure nutrients, recycling them and getting them back into the system to replace what's removed as effectively as possible. And so with that, I will thank Luke and Dean for the opportunity to participate in today's webinar, and happy to answer questions that you folks in the audience have. Thank you.
All right, folks. Okay, folks, all good here. Thank you, Dr. Schoenau, for that excellent presentation. We'll move now to the Q&A session. So for folks in the audience, if you have a question, please put it in the question box in your control panel, and I'll do my best to get through as many as we can as time allows. We'll wrap up this session by noon. So our first question was about spreading urea in the fall. When spreading urea in late fall on a forage stand, especially before snowfall, is there significant nitrogen loss during the spring melt?
I think that if you're putting that urea on in late fall, then you get your typical snowfall that would come in November, let's say, and it's going to lay on that forage stand and infiltrate and move in as it's able to do. Typically, a forage is pretty dry in the fall of the year, and maybe not recently cut. You got a lot of material standing there, so that's going to keep that snow in place. And as it melts, it's going to move that urea into the mineral soil beneath it. Once that urea gets into that soil and it's cool, it will tend to it'll tend to stay there as urea. It may undergo a little bit of hydrolysis, convert to ammonium, but I think that generally you can expect pretty good retention from that application strategy. If you put the urea on really early on in the fall, and it sits there on the surface and the soil is warm, the thatch is warm, maybe you get a little bit of rain, but not that much, especially under, maybe this might be more typical of a drier region, you can get that hydrolysis taking place. The urea is still sitting there on the surface, and it is susceptible to volatilization losses. So I kind of like this when the soil's cool, it sits there for a while on the surface, but the urease activity is low because of the cold temperatures. Snow comes along, it's still early enough for that snow to melt and carry that urea into the soil. I think you stand a pretty good chance of getting a pretty efficient application of that nitrogen in terms of it staying in the soil and being recovered by the forage when it starts up growing the following spring.
Thank you. Another question from the audience. He says, thanks for sharing your expertise. A farmer observes declining alfalfa stands in a mixed grass field. Soil tests show marginal K and S. What steps would you recommend to restore alfalfa dominance? And what soil tests or other assessments should be conducted before implementing a fertilization program for forage?
Yeah, I say, obviously in that case, the macronutrients have been looked at, and potassium and sulfur have shown up as a limitation. I'm guessing it may be an area in northern northern Saskatchewan agricultural area in the gray soil climatic zone, gray luva soils, maybe sandier texture soil. And probably in that case, you know, you may look at in that alfalfa stand, broadcasting some potash onto there to supply some potassium. Again, potassium's kind of like phosphorus. It's not highly mobile, so you maybe wouldn't get as good a response from the potassium as if you were placing it into the soil, but still a broadcast application of potash on that alfalfa stand can work well, I think, in providing some recovery from that low potassium condition in the soil. Alfalfa has some feeder roots, surface feeder roots, so it's going to be able to access that. Eventually, that potassium, I think, is going to make its way down deeper, like we find with phosphorus. In the case of the sulfur, you know, ammonium sulfate, I probably wouldn't pick as an application for alfalfa because you're applying the nitrogen there that really isn't going to be of much benefit if it's a stand that has a high proportion of alfalfa. But if it's lower in proportion of alfalfa, the grass may benefit from some of that nitrogen, and you've got that sulfur there in the immediately available sulfate form in the ammonium sulfate to provide a boost of sulfur, not only to the legume, which is probably going to need it more, but also to the grass. And some folks also will broadcast elemental sulfur onto a stand that's been identified as sulfur deficient. And not all of the elemental sulfur is going to oxidize to sulfate in the year of application. But it is what we might consider a slow release source of sulfur that over time that elemental sulfur will oxidize to sulfate and gradually release sulfur into the available form for that legume if it's deficient. So I mean, I think your soil test is a very good tool. Again, I think you can look at both extractable amounts. I think another very effective way is to look at supply rates using the PRS probe technique. It's a kind of a dynamic measurement, and I think a dynamic measurement of nutrient availability can be especially important in a forage stand because it oftentimes in a forage stand, you don't find a lot of nutrient in the available form at any one time. But more importantly, what is happening over time because of that higher organic matter content, you're getting nutrient that is slowly being released through microbial decomposition into the inorganic forms, and the PRS probes will pick that up.
Thank you. Another question we have is, has there been any research comparing drilled in P versus broadcast P?
Broadcast versus placed P. Yeah, I think there was some work that was done by Dr. Molly at Melford Ag Canada a few years back, and he found that the broadcast phosphorus tended to be less efficient than the drilled in or banded in, because again, that lack of mobility of the phosphorus meant that more of that phosphorus tended to be hung up in the surface. So it took longer for the roots to finally get there and be able to find it and access it. So broadcast is okay. It's a way that you can get some phosphorus on there if you determine, yeah, that's really what's holding that stand back. Broadcast that phosphorus on there, but certainly from an efficiency standpoint, especially greater recovery over a shorter period of time, actually bringing that phosphorus fertility up to the desired level right at the start when you're establishing the stand, I think was shown to be the most effective strategy. It requires an investment in phosphorus fertilizer up front, maybe 50, 60 pounds of P2O5 per acre right up front, but you've got enough on there that's going to hopefully last the life of the stand.
Thank you. Another one, can liquid hog manure be applied at rates high enough to replace phosphorus removal in alfalfa stands on an annual basis?
And that's a good question. And I think certainly the phosphorus that can be applied as manure, and in particular a liquid source like dairy manure or liquid hog manure, could be applied at a high enough rate to replace the phosphorus. But the trouble is that you've also got a lot of nitrogen in there as well, especially the hog manure, a lot of nitrogen in the available form. And unfortunately, that nitrogen that you add is going to be taken up by the alfalfa, and it's going to be taken up in lieu of the plant actually fixing it and obtaining it from the air. So you're not going to see much benefit from the nitrogen that's contained in that manure in your forage legume stand. And I think back to some work that we did with PAMI back in the 1990s with the liquid swine manure on alfalfa stands in northeastern Saskatchewan. I think it was the Valparaiso area. And I recall that we really didn't see much yield benefit from that liquid swine manure injected into that alfalfa. It wasn't a highly phosphorus deficient stand to begin with, and the nitrogen was really of very little benefit because the plant just used it instead of fixing it. If it wasn't there, it carried out the fixation.
Great. What are some signs that a forage stand is underperforming due to nutrient limitations rather than environmental stress or stand age?
Yeah, and I think that's kind of gets into the diagnostic side of it. And here I think you know, a good tool that a person could use. A soil test is one of them, but in particular a tissue test, taking a sample of the above ground plant material and having it analyzed for nutrient concentrations, I think will give you an idea if there is a deficiency, limiting there relative to its yield potential, a critical or optimum concentration that you'd like to have in the plant. If it's below that, the nutrient concentration of the plant below that critical level, and to what degree, gives you an idea of the relative severity of limitation and differences amongst the nutrients. So yeah, I think you know, a visual is a good, you know, can be used as a good first clue, but I think a tissue test is really another good way to determine, ascertain if in fact there is a deficiency or deficiencies of nutrients that's holding back that forage stand.
Thanks. And we have a question about the bale grazing versus the dry lot study, and they were wondering if the results accounted for wasted feed.
In a sense, they did, because the wasted feed, the feed that remains uneaten, also contributes to a supply of nutrient in the soil where that feed was laid down. If it was a bale placed down for bale grazing, or whether it was put out in the field using a bale processor. And I think that Paul also measured that as part of his thesis work. And I think I'd probably have to go back into his thesis to actually give a number for that. But yeah, there is an uneaten feed component, and that translates into, you know, a potential effect of efficiency of utilization by the animal as it's eating out there in the field. But the other angle of it is that the feed that remains uneaten sitting there in the field also contributes to a supply of nutrient as that uneaten feed undergoes decomposition into available forms by microorganisms in the soil out there in the field.
Okay, thanks. And still on that topic, did you leave a check strip to assess the effectiveness of the fertilizer and manure application?
Yes, there was a control in all of these where there was no manure applied or no animals at all out there in the field, and that was what I had shown there. I think in that one graph of that, if you look all the way over to the left hand side, there's what we call a control, which is no animals, which means no infield feeding, nutrient contribution, and no manure applied.
And kind of a general question, I guess, but how does fertility management change over the lifespan of a forage stand, from establishment to mid-rotation to declining years?
Yeah, and I think that's a good point. And I think if you're thinking about a scenario where a producer would go out and seed a forage into a stand, or seed a forage, establish a stand in a soil without any added fertilizer, and maybe because it had pretty good fertility to begin with, residual nutrient left behind from past additions of fertilizer, for example, in annual cropping. You know, I think then you may anticipate that if it was such a field that had good fertility to begin with, you'd expect to see good productivity at the beginning. As the productivity tended to decline because of continuous crop removal, if you're haying that field, then I think you'd start to look at some ways that you would replenish that nutrient that you've been taking out over a number of years, and look at each nutrient individually and make sure that you were applying the appropriate balance to put back in what you were taking out. So, you know, in terms of fertility management over time, hopefully you're okay at the outset, but as the field matures and you're taking lots of nutrient out and you know roughly what your bale yields are, you can calculate how much nutrient you're removing per acre. You know that if there's no legume in there, there's no nitrogen coming in from fixation, you know, and all those nutrients that are going out, eventually they're going to have to be replaced if you're going to maintain the productivity of that field. And that's going to come down the road as that stand matures, or as time goes on and that stand gets older.
Thank you. And are there any special considerations for managing fertility in saline or marginal soils?
Yeah, that's an interesting question, kind of one that we've done a fair bit of recent work on, related to taking those saline soils and seeding them down to a salt-tolerant forage, like salt-tolerant green wheatgrass. And I think in the work that we've done, we found that those saline areas often have really quite high levels of available nutrient, because they've probably in many instances been part of a field that's received fertilizer every year, but actually growing very little crop. There's been very little crop removal. As a result, weeds may have grown, but nutrients have recycled out of those weeds back into the soil. And so what we found is that when we established salt-tolerant green wheatgrass on these saline soils, there really were no nutrient limitations that we observed, and we didn't put on any fertilizer at it. We had some amendments, some manure amendments as treatments. We had some other humic materials on there that were part of this study, but no added commercial fertilizer. And it seemed like what happened over time is once that forage, that salt-tolerant forage established on that salt-affected soil, it was actually able to tap into and use those residual unused nutrients from previous years' fertilizer applications and use it to grow very well, along with the shallow water table that was present in those saline parts of the field that we used for our experimentation. So I would say, test that saline soil when you're establishing it, find out how salty it is, and that's important to know when thinking about what kind of species you might want to try to get growing there, and also get the available nutrients measured. And I think you probably will find they'll probably be pretty high. In this study, with the salt-tolerant grass seeded into the saline area, we did find after about 5 years that we did benefit from an application of nitrogen, because we were pulling off after 5 years some pretty high forage yields out of that saline area, because of the ability of that salt-tolerant grass to actually grow as well on the saline area as it did on the non-saline area. So yeah, same kind of principles apply, I think. Soil test, and also think over time about what your yields you're getting out of there and what that equates to in nutrient removal.
Great, thank you very much. Yeah, thanks, Dr. Schoenau, for your time and the great information you've shared today. It is noon, so we'll wrap it up, but thank you for everyone who joined us. A few final reminders before we close the session. A recording of today's session will be sent out by email along with a survey. Please take a moment to fill that out. Your feedback is greatly appreciated. If you have questions about today's topic or anything related to forage, range, or agriculture in general, please reach out to your local Saskatchewan Agriculture Regional Office or the Agricultural Knowledge Center at 1-866-457-2377. We're happy to help connect you with the right support. We hope to see you all at our next webinar, Brush Management on the Prairies, coming up on Tuesday, April 15th at noon. Thanks again and have a great day.